Hello, everyone. Thank you for having me. Thank you to Dr. Bain for that introduction. It's really my honor to be here, part of this brisk 2 days of covering just the incredible breadth of emerging work in precision health. So today I'm going to talk about the MRI, and it's really a very exciting time to be talking about the MRI because it's 2017 this year. 40 years ago, exactly 40 years ago, 1977, was the year that the first MRI of a live human was taken. Now, I'm going to show you that image. And this is what it looks like, July 3rd, 1977, 4:45 a.m., when a postdoc was very hard at work. And this is what it looks like. This is a cross-sectional image. Who can point out the heart for me? It's in the center of the image. This is an image of cross-section of a chest. So the heart is in the middle. We see the lungs on either side. And then we see the whole body wall and the vertebra. And this may not look very impressive to you today in 2017. But at the time, it was deemed a fantastic success. Yeah. These are the original notes from some of the scientists who was working on this. And I'm just reading. First human image, complete and amazing detail, showing the heart, the lungs, the vertebra, and the musculature, July 3rd, 1977, 4:45 a.m. Now, in 2017, of course, 40 years later, the rest is history. There's been a proliferation of MRI modalities. We have T1, T2 flare, but also things like MR spectroscopy, diffusion-weighted imaging. We have molecular imaging. Also, at the same time, the scan times have been reduced to the point where we can take images of organs in motion, like the heart. And now we have 7 Tesla scanners, 11 Tesla scanners. I don't even want to know how high that number is going to be. It sounds very scary to me. And at the same time, we're able to achieve nanometer spatial resolution. Some of that work was actually done here at the University of Illinois a couple years ago, where scientists showed that we can go from millimeter to the nanometer scale. So we are able to see human tissue in an unprecedented level of anatomic detail. And of course, there's this big success story, but there's actually another side of imaging. There's a dark side of imaging, a side that researchers could not and did not anticipate in 1977. And that is that you see that the deeper you go, as you go from tissues to molecules, we see that the data becomes more complex, not less complex. It seems that the level of complexity increases almost exponentially, and it becomes harder for the naked eye to make sense of what we're seeing, not easier. And some of this complexity is so high that these images can almost look inscrutable. So, even though 90% of all digital healthcare data is in the form of imaging, there's actually a lot more information in these images than we've been seeing. Now, let me give you an example of what I mean. These are images from the Osteoarthritis Initiative. This is a database that contains thousands of knee MRIs of both diseased subjects and healthy subjects. Just as a quick review of the anatomy, I showed a picture of a knee. So we have the 2 bones, the femur and the tibia, and the cartilage is just the cushion, the shock absorber between the 2 bones. And we're looking at cartilage images here, different image per subject. And when these images were taken, none of these subjects had any evidence of any disease in the knee, no arthritis, no pain, no radiographic changes, completely healthy. But by following them up 3 years over time, we know that one of these groups goes on to develop clinical osteoarthritis, bone damage and pain, and the other group doesn't. And the question is, 3 years before that happens, by looking at these cartilage images, can we tell which group is which? See, the problem is that our eyes can't seem to detect the difference between these two groups. Let me show you another set of images. These are brain images, one image per subject. And these were taken shortly after these subjects suffered concussion. So after they suffered their concussion, we measured their reaction times. The 5 subjects with the fastest reaction times are on the top row, and the ones with the slowest reaction times are on the bottom row. And again, we run into the problem. We can't seem to detect the difference between these groups of subjects just by looking at the images. Now, of course, we don't even know if this difference is there to begin with. But if it is there, it seems that we can't see it. So what we're seeing here is just the enormous complexity of the data. And really, what we run into is trying to find, as the saying goes, a needle in a haystack. But then there's a twist, because we don't even know if the needle is there. So we're trying to disambiguate meaningful information from background variability and noise, and we don't even know if that information is there. So that seems kind of a chicken and egg problem. So how do we even begin to attack this? So the question I wanted to investigate was, if the information is hidden by noise, can we still unmask meaningful diagnostic information? And we've been hearing that machine learning is a possible way to do this. Certainly a lot of companies have looked into this area, both big and small corporations. But we'll see that it's not, machines have difficulty with this too. And let me show you what I mean. Let's look at these images again. One of these groups, again, will go on to develop osteoarthritis 3 years down the line with radiographic changes in pain, and the other group won't. These are their images of knee cartilage 3 years before that happens. Now, we can try to train a simple classifier, just using texture features. Let's say we quantify Tamura texture statistics, histogram statistics, Zernike polynomials, just 100 different texture features. And we feed that into a simple linear classifier. Well, we're able to achieve about 76% accuracy on new data that we've never seen before on predicting whether that person will go on to develop osteoarthritis. And that seems OK. But the thing is, if you feed in age and BMI, just 2 numbers only, you get about 72%. So it's actually pretty comparable. And there is room for improvement. So I think what this shows is that just feeding in the images pixel by pixel oftentimes also is not the best way to teach the computer to be able to interpret these images. So now I'm going to present some preliminary results on one way that I sort of attack this problem of trying to extract meaningful information from the background variability. And the first thing I did was I took the images and I standardized them by mapping the curved shape of the condyle onto a flat plane using a mathematical transformation. The second thing I did was I thought that if a computer has difficulty understanding these images pixel by pixel, maybe we can teach it to understand interrelationships and patterns within these pixels. And so one of the ways that I did this was I used the mathematics of optimal mass transport. And the way that it works is that on one hand, you have a pile of dirt. On the other hand, you have a castle, same mass. And you're trying to find the most parsimonious way to rearrange the particles of dirt to look like the castle. Now, you can imagine that we can do the exact same thing for images by just treating the intensities as pieces of dirt. And we can compute the transformation needed to move the pixels and rearrange the pixels in one image to look like another image. And this is useful because we can use this to transform images from the raw pixel data to a representation that a computer might have an easier time with. So this is the transform that we built, transport-based morphometry. And the way it works is that on one hand, you have images in image space. And you see brain images here because that was some of the original work. But you can use any images, any form of images here. And so we used cartilage here, obviously. So you have images in image space that are not very separable by looking at them by eye. They're not very separable if you look at them pixel by pixel. But you can transform them to a representation where every image is represented by a point in a very high dimensional space. And the thing about this transform, the idea here is that we're not looking pixel by pixel. We're really trying to measure distance between the images. So the idea is that the images that are more similar will be clustered together on this high dimensional manifold, and the images that are more dissimilar will lie farther apart. And in this manner, what we're looking at is distance, not raw pixel data. And the idea is that the computer would have an easier time, presumably, picking out the differences in an alternate representation. Now, there are a lot of mathematical transformations that exist. We've heard of Fourier transforms, wavelet transforms. So this idea of transforming data to another domain to enhance separability, it's not new at all. But the part that is new, and what I think is the coolest thing about transport-based morphometry, is that it's an invertible transformation that doesn't lose any of the data. So when you transform the images from pixels to this representation high-dimensional space, yes, it might make the data more separable, but you can also recover that image uniquely, and you can visualize what it looks like. Now, this is useful because this makes transport-based morphometry more than just a black box technique where you feed in images and it gives you a number. You can invert the decision boundaries that the classifiers learn in the transform space and actually visualize the changes that the computer is using to make the classification. So you're probably wondering how this scheme fares on the data that I've shown. It turns out that on those images that were not very separable by eye, not very separable if you look at them pixel by pixel, if you transform them to the transport space where we try to figure out distance between the images, they're perfectly separable, shown by this histogram. Now, in fact, they're so separable that if we use this data to learn a decision boundary, and we apply this decision boundary to classify new samples that this computer, this algorithm has never seen before, then we can achieve up to 86% accuracy in predicting whether a subject will go on to develop clinical osteoarthritis 3 years down the line. And this is a clinically useful accuracy. The other thing I'd like to just bring up is this is only trained on 70 subjects. So imagine that this will only get better and better, and this model will get more robust as we feed in more subjects. Now, we could stop here and say that this is interesting work, and now we can diagnose osteoarthritis, and that's what a lot of machine learning techniques, that's where a lot of machine learning techniques leave it. That, oh, we can classify with X% accuracy. This is as good as doctors, or almost as good as doctors, we're done. But that wouldn't be very satisfying, would it? I bet everyone's dying to know what it's using to make this classification. So I mentioned the coolest thing about transport-based morphometry is that it's fully invertible. So you can actually invert this decision rule that it learned and look at the actual images. And so if we plot these images, I'll explain the slide. Here on the x-axis, we go from 4 standard deviations towards a control side to 4 standard deviations towards the progressor side. 0 represents the average image. On the y-axis, we have slice number. Remember, these are 3D images, and we're slicing through the knee like a loaf of bread. These are sagittal slices. So as we go from one end, as we go from the control end to the progressor end, and let's say we look at slices 4 through 6, and just scan across from control end to the progressor end, we see that there's an area of redness that kind of develops in the center of the image. And these are colorized images, so redness here represents brightness, and brightness represents water. And just as potholes on the road collect water, this seems to suggest that there's already a focal weakening at that location that's collecting the water. And this is 3 years before any symptoms. And this is what the computer is using to predict whether someone will develop osteoarthritis 3 years down the line. Now, very similarly, we can look at the lateral condyle, and we also see differences in slice numbers 4, 5. If we just scan across in the distribution of the red, it seems to be a little bit more diffuse or spread out on the progressor side. Now, so this is where we have sort of opened up the black box and we actually look at what the computer is using to make the determination. And I think in summary, what this shows is that AI in healthcare, it's not just a tool for, it's not just about robots replacing doctors. It's about doctors strapping on robotic suits, becoming bionic doctors to see more than the unassisted human eye can see. It's about finding evidence of disease where we didn't know where to look, and we didn't know we didn't know what these changes would be, and using them for tasks of objective diagnosis, early diagnosis, and even maybe just understanding the process, maybe just understanding what a damaged cartilage might look like 3 years before it becomes an osteoarthritic knee. So with that, that brings me to the end. These are the references that I used, and thank you for your attention.